Let's try problem 15.20. In the deep ocean, a water wave with a wavelength of 95 meters travels at 12 meters per second. Suppose a small boat is at the crest of the wave, 1.2 meters above the equilibrium position. What will be the vertical position of the boat 5 seconds later? Okay, so we just have a boat on a wave. So let's say that's my wave, and we're told that's at the crest. So let's draw my boat up here. So let's say that's my boat. And let's say this is the equilibrium position. So the crest is going to be the amplitude, right? So let's start writing down some more variables. So we're told that it's at the crest, which is the amplitude, so 1.2 meters. We're given a wavelength of 95 meters, so lambda is equal to 95 meters. And we're told that this wave has a velocity of 12 meters per second. Okay, and we're asked to find the vertical position of the boat 5 seconds later. So what we're going to need is to use our general displacement wave equation, which is y of x comma t, so it's a function of x and t, is going to be equal to the amplitude times the cosine of 2 pi times x over the wavelength, plus or minus depending on which way the wave is traveling. So in this problem we're going to assume that it's traveling in this direction, and so to the right is negative. So this in here is going to be negative for us, but let's just write down the general form. So plus or minus time over the period. Okay, so we know some of these things. We know the amplitude, we know the wavelength. We'll figure out x when we move forward. We know the time, 5 seconds later. We just need to figure out this t, which is the period. And so if you remember, v is equal to, so the velocity, so this velocity, it's right over here. So velocity can also be written as the frequency times the wavelength. And so we know the wavelength, and we know the velocity, and so if we solve for a frequency, we can easily find the period, right? Because the period is just 1 over that. So if you remember, where should I write this? Let's do it right here. Frequency is equal to 1 over the period. So just rearranging this over here to solve for frequency, we get frequency is equal to the velocity over the wavelength. Or if we want the period, we just flip this fraction, right? Because it's 1 over t. And so t is equal to the wavelength over the velocity. And so if we plug the wavelength in, which is 95 meters, over the velocity, which is 12 meters per second, we get units of seconds, and we get t is equal to 7.92 seconds. So that's the first part of this problem. So now we have everything in here, so now we just need to fill in. But if you realize, we need to figure out an x and a t. Well, we need to figure an x, we need to figure out where we're going to solve this for. So just for ease, we're not worried about the horizontal position, so let's just pick it as 0, right? I mean, there's no harm in picking x just to be 0. And so what's going to happen is this wave's going to travel down, and we're saying that it's going to be at 0. So let's just go ahead and plug in. So y, we're calling just x 0 because we can. 5 seconds, and we're saying t is 5 seconds. And this is equal to the amplitude, which is 1.2 meters. Let's leave off the units for now just to make it clean. Times the cosine of 2 pi times, we're saying x is 0, so this first part just becomes 0. And we said it's traveling to the right, so it's negative, minus time, which is 5 seconds, over the period, which we just solved for, which is 7.92. And then we plug this into our calculator, and make sure you're in radians again. This comes out to negative 0.81 meters. And so this boat is going to go down, which is good, right? We got a negative number, which means that the boat is going to move down, which which has to happen because it's at the crest and it has nowhere else to go, and this wave is traveling to the right. So this wave is going to travel, and the boat's going to sink down negative 0.81 meters 5 seconds later. And that's problem 15.20.